It's the All Things Strange podcast. I am your host, Agent Anderson. Come along as we examine UFO sightings, conspiracies, and all things strange. You can find all of our wonderful links in the description on the Linktree, where you can find our Patreon, our Discord, our merchandise, and more. This week's episode, the Multiverse. All right, this is a really fun one. I had a lot of fun doing the notes for this. A lot of really fascinating ideas that I went over, and I don't even have time to talk about all of them. But before we get to it, don't forget we've got 2 wonderful tiers of patronage for you. Join Patreon for early access, after hours, bonus episodes, and that's just the first tier, for a measly $3 a month. The second tier will get you the ability, right? I don't know, whatever. You get to vote on upcoming topics such as this one. All right, let's do it. There are many ideas that could be called the multiverse. From science-based theories to philosophical musings, many have wondered and imagined places existing outside of our own realm. All right, guys, buckle up because this one gets weird. And also, just a quick disclaimer, I am not a scientist, so I'll probably get some things wrong. I'm just doing my best here to make a podcast, so apologies for any mistakes I make in terminology or getting science incorrect. All right, now one thing that's going to come up a lot in this episode is the universe. I know, right? Big surprise. It's just for people unfamiliar. It's generally believed that the universe started with a big bang, and it's still expanding today. There are different theories out there about how it began, how it's going to end, but this is the one I learned about in school, the Big Bang, so that's the one I believe to be true. Also, Pluto is a planet. So anyways, during the Big Bang, the universe expanded rapidly. Well, just after, I guess. Just after it went pop, it expanded rapidly. Then the expansion slowed, but then it started to accelerate again because of dark energy, which is another way of saying we don't really know why. It just did. So the universe is still expanding and at an accelerating rate. We know this from something called redshift, which is the light wave version of the Doppler effect. Basically, when something moves away from our observation point, the light wavelengths are stretched out. The same thing happens to sound with the Doppler effect, which probably you're familiar with. As a sound source travels away, the sound waves are stretched out and the pitch is lowered. Conversely, as it approaches, the pitch is raised and the waves are compressed and you get a higher pitch. You can hear this easily if you're standing on the side of a road as cars pass by. It's easier to notice if one of them is like honking their horn or something. But all of the sounds of the motors, the tires, etc., they will all change pitch. Now, by the same token, when light is moving away from us and the wavelength is stretched out, the color of the light moves toward the red end of the spectrum, hence the term redshift. If it's moving towards us, it's blue shifted. It may sound trivial, but this simple observation has given us so much insight into our universe. It tells us that the universe is expanding and how fast. This allows us to calculate the approximate age of the universe. Gravitational redshifting, where photons are affected by a gravitational well, like, a planet or star, they lose energy because of that gravitational pull. Those are redshifted or blue shifted if they're pulled towards it. They tell us all sorts of things about the object, such as, its mass. Redshift measurements allow us to test general relativity, and on and on and on. It's really quite astounding what they've used this simple idea for. If anybody asks you an astronomy question and you're not sure, just say redshift. There's a reasonable chance that you might be right. Probably not, but you know. How did they first determine the age of the universe? Boom, redshift. I think? I don't know. And you're probably right. Yeah, it just boggles my mind how such a simple idea is stretching out a wavelength has led to such a vast portfolio of scientific discovery. It's really quite fascinating. And it would be really far afield of kind of what I talk about on this show, but it's really, really quite interesting. So anybody who's into that sciencey stuff, I encourage you to go look at redshift because it's really interesting stuff. So it applies not just to visible light, but all electromagnetic radiation. For instance, a gamma ray can be perceived as an X-ray. Visible light can turn into radio waves, and so on and so forth. You can look at a chart and see what stuff is going to shift where. All right, now let's talk about the cosmic microwave background radiation. Now we're going over a couple of basic things like definitions, just to refresh my memory and refresh your memory if you haven't read about these things in a while, because we will be talking about these later on in the episode. That way I don't have to stop in the middle of something and like define what it is. So the cosmic microwave background radiation fills all space in the observable universe. It was accidentally discovered by radio astronomers Arno Allen Penzias and Robert Woodrow Wilson in 1965. And it's been theorized before then, and it's been discovered by other people. They didn't really know what it was, but they knew they were seeing something weird in their radio, their radio telescope or whatever it was. So this is the most important evidence of the Big Bang. It supports the idea that the early universe was an opaque fog of dense hot plasma of subatomic particles. The universe expanded, and the plasma cooled enough for protons and electrons to hook up and make hydrogen. Ooh, giggity. The new hotness, the cool hydrogen atoms, didn't throw off thermal radiation like the plasma did, and thus the universe became transparent with a subtle, hard-to-detect cosmological background radiation, or microwave, or CMB, depending on how you want to say it. It's the same deal, So the CMB is mostly uniform, but there are small variations. These variations tell us a lot about the universe. For instance, they hint at the curvature of the universe and can be used for, they hint at other things as well. Also, the CMB is redshifted in all directions, which tells us that the universe is expanding in all directions. So if it was only redshifted in one direction, that might mean that our neck of the universe is stationary, but over there, the other part over there is moving away from us, or towards us if it was blue shifted, right? But this tells us that every direction, everything's getting further away from each other. Really weird. So that's just some background stuff. I might do some more background stuff as we go as needed, but I just wanted to throw out just those basic ideas. Now, the idea of a multiverse goes back a long time. To the first known mention of something is Anaximander in the 6th century BCE. Anaximander, I'm not going to even try. It suggested that infinite worlds exist, and there have been other, philosophers throughout the years who suggested things similar to a multiverse, or multiple universes, or multiple worlds. Fast forwarding a little bit, in 1895, American philosopher William James used the word multiverse, but in a completely different context than what we're talking about in this episode. But also in 1895, this topic, among other things, was discussed in a scientific debate between physicist Ludwig Boltzmann and mathematician Ernst Zermelo. I wonder if there are any transcripts of that debate. That would be interesting to read through, although I don't think my German is quite up to snuff, assuming they did it in German. Those are German-sounding names. In 1952, Erwin Schrödinger, the guy who tortured cats, said in a lecture that his equations showed that several different histories were happening simultaneously, and this is known as superposition. So his equations say that there are multiple possible paths that something can take, but also that they are taking those multiple paths. We're only seeing one of them, or something like that. So according to him, there are multiple parallel universes that exist simultaneously. There's more stuff like that I'll talk about later. So beginning in the 20th century, scientists began to have both the theory and capability to start looking for evidence of a multiverse. And I won't go over all of the stuff that, I mean, it would take forever and it would be multiple episodes to go over all this stuff. But more recently, data from the Wilkinson microwave anisotropy probe was interpreted to suggest that our universe had collided with another parallel universe. Planck satellite data, which was more sensitive than the WMAP, seems to dispute this. But still, we had somebody with actual data that looked like it might indicate a multiple universe or a multiverse. In 2015, Dr. Rangaram Chary from Chary, I'll spell that because I'm not sure how to pronounce it, Dr. Ranga-Ram Chary, so Chary maybe, Cherry or Chary. Dr. Rangaram Chary at Caltech analyzed the cosmic radiation spectrum, the cosmic background radiation that I was talking about, just after the Big Bang happened. He found a signal 4,500 times brighter than expected. Quote, "This signal, an emission line that arose from the formation of atoms during the area of recombination, is more consistent with a universe whose ratio of matter particles to photons is about 65 times greater than our own. There's a 30% chance that this signal is noise and not really a signal at all." That's 30, guys. There is a 30% chance that the signal is noise. That is not trivial. However, it is also possible that it exists because a parallel universe dumped some of its matter particles into our universe. If additional protons and electrons had been added to our universe during recombination, more atoms would have formed, more photons would have been emitted during their formation, and the signature line that arose from all of these emissions would be greatly enhanced. Many are skeptical of this evidence, including Dr. Rangaram Chary, but the possibility remains. I don't think I quoted it here, but Dr. Rangaram Chary said something of the order of like, well, if we're going to have multiverses, we're going to need some pretty big evidence, and this isn't really that big of evidence. But just imagine that. What could that possibly be? Maybe we're in a scientist's laboratory, and you just have somebody creating a universe in their, in their lab, and they're just kind of, we need a little bit more of this, a little bit more of that, and they're just kind of like dumping stuff in as it forms. I don't know. Why not? Many scientists are skeptical of the idea of a multiverse altogether and consider it more on the side of philosophy rather than science. Basically, the idea is you can't disprove the existence of the multiverse, therefore it can't be tested and isn't a part of science. It's more of a thought experiment, kind of like, you can't scientifically disprove God, so it's not science. Same thing. You can't disprove many of the ideas I'm about to talk about, so it isn't really all that scientific. But to those skeptics, I say, poppycock. We can't test for the multiverse because we haven't figured it out yet. That doesn't disprove anything. But to be fair, it doesn't prove anything either. So here's a quote just to represent a skeptic who, this is not the same thing as like a pseudo-skeptic when it comes to UFOs. These are people who are rightfully questioning ideas in the realm of science, and I want to represent their viewpoints as well, even though I don't want to spend too much time on it because that's not fun. Come on, we want to have fun here. So anyways, here's a quote from Paul Davies from his book, A Brief History of the Multiverse. "For a start, how is the existence of the other universes to be tested? To be sure, all cosmologists accept that there are some regions of the universe that lie beyond the reach of our telescopes, but somewhere on the slippery slope between that and the idea that there is an infinite number of universes, credibility reaches a limit. As one slips down that slope, more and more must be accepted on faith, and less is open to scientific verification. Extreme multiverse explanations are therefore reminiscent of theological discussions, indeed invoking an infinity of unseen universes to explain the unusual features of the one we do see is just as ad hoc as invoking an unseen creator. The multiverse theory may be dressed up in scientific language, but in essence, it requires the same leap of faith. So there's a lot of discussion similar to that. Now, I don't think that's entirely true because we do have scientific theories that can be interpreted or suggest a multiverse, and we do have some evidence that it might exist. But on the other hand, he is correct here that we can't really test these things currently. But maybe someday we can. I don't know. I looked through a lot of stuff for this episode, and it's kind of interesting how many random things touch on the idea of a multiverse. I can't mention them all, but one of the ones I will mention later is the inverse gambler's fallacy. And it's more of a thought experiment. It's not really a scientifically based idea, but it's still pretty interesting. All right, so let's get to some different ideas or versions of multiverses. This first one is definitely based in scientific observation. It's the antimatter universe, or the baryon asymmetry problem, if you want to read up on it yourself. So baryonic matter, baryonic, by baryon asymmetry or baryonic matter, that basically just means normal matter. This microphone I'm talking into, the air you're breathing, molecules, all that stuff, just regular stuff, regular matter that floats around the universe. Non-baryonic matter is different, stuff like neutrinos, free electrons, dark matter, stuff like that. Antibaryonic matter, or what's more commonly referred to as antimatter, is the opposite of normal matter. It's composed of antiparticles. For example, its electrons are positive and its protons are negative, whereas our matter, it's all arbitrary anyways, right? But our matter is the opposite way around. Protons are positive and electrons are negative. So it's like normal matter, but it's the opposite of normal matter as far as charge goes. Also, it gets a lot more complex than this, but I'm trying not to get too bogged down in things when I was taking my notes because we don't want to spend an hour and a half talking about antimatter. It's probably a bit much, for what I want to do. So antimatter can occur naturally in rare cases, such as cosmic ray collisions and certain types of radioactive decay. It can also be created in particle accelerators in very small amounts. Either way, it's extremely rare stuff. But here's where it gets tricky. Here's where it gets weird. Scientists say that there should be more antimatter in the universe. In fact, the Big Bang should have produced equal amounts of matter and antimatter. But if that was the case, the universe would look very, very different than it does today. And the reason for that is when matter and antimatter meet each other, they annihilate each other. Just poof, gone. The two cannot coexist. So if the universe had an equal amount of each, they should have annihilated each other, and therefore we wouldn't be here at all. Or at least the universe would be very different than it is now. Now, I won't go into all of the reasons why that is, but it's not like, that's not controversial as far as I can tell. That's basically, science fact. So they're pretty sure that that's the case, that there is missing antimatter. There's no scientific consensus as to why the antimatter is missing, however. Leading possibilities are that the laws of physics were different during the Big Bang, causing this asymmetry, or what we know or understand about physics may not be totally accurate, so that, when matter and antimatter annihilate each other, maybe more regular matter is left over for some reason that we don't understand. Or, more relevant to this episode, maybe the two were somehow separated at birth. If the matter and antimatter somehow separated, then there could be anti-galaxies out there. These would appear identical to regular galaxies because they would produce photons the same way that regular galaxies produce photons, and therefore we could observe them the same way we observe regular galaxies. However, if there were anti-galaxies, they would annihilate normal matter when the two met. This would be detectable. So you have a galaxy out there, and it would come into contact with regular matter, and that would leave a trace. We would be able to see that happening, but nobody has ever detected that happening. So therefore, there probably is not a pocket or pockets of antimatter somewhere in our universe. And another possibility, again for this episode, is the mirror anti-universe. So when the Big Bang happened, it could have happened in two different directions. Antimatter and matter became completely separated and went into, let's say, different directions. I'm just trying to visualize this. I don't know that direction even is relevant when you're talking about a universe that creates its own space-time, right? So here's a quote. The anti-universe would flow back in time from the Big Bang, becoming bigger as it does so, and would be also dominated by antimatter. So there would be regular matter in it on rare occasion, just like we have antimatter on rare occasion. Now, I don't know what that means about flowing backwards in time. It sounds pretty weird, though. I warned you, this one was going to get weird. It's continuing on the quote, its spatial properties are inverted if compared to those in our universe, a situation analogous to creating electron-positron pairs in a vacuum. This model proposes that temperature fluctuations in the cosmic microwave background are due to the quantum mechanical nature of space-time near the Big Bang singularity. Now, I can wrap my head around, stuff has gravity and it pulls other stuff towards it. Light travels from here to there, stuff like that. But when you start getting into quantum mechanics, I get started scratching my head or something. I get a little confused. So the temperature fluctuations in the cosmic microwave background, that I mentioned that earlier, that there are faint detections of, it's mostly homogeneous, but there are areas that are, not. There are variations, subtle variations, and that leads us to many different possibilities, what could have caused that, and multiple things could have caused it. So continuing on with the quote, this means that a point in the future of our universe and a point in the distant past of the anti-universe would provide fixed classical points, while all possible quantum-based permutations would exist in between. Quantum uncertainty causes the universe and anti-universe to not be exact mirror images of each other. So this could also explain the missing dark matter problem, because a universe-anti-universe pair would produce large numbers of super heavy neutrinos, aka sterile neutrinos. Sterile neutrinos is a type of subatomic particle that only interacts through gravity and no other force. These particles are currently only theoretical and have never been found. But if we have these two separated universes, that could explain the missing dark matter problem. So it works, and it sort of fits in with some evidence of what we have going on in our universe, but we don't have proof of it yet. So there you have it. It's entirely possible, but not proven, that there's a mirror universe out there somewhere. Is there an anti-me recording an anti-podcast right now? Or, as it said in the above quote, they're not exact mirrors of each other and they're completely different from one another. I don't really understand all that stuff, but it also said that because of quantum uncertainty, there could be any number of permutations. Also, the time thing is kind of freaky. I think it just means that the anti-universe would be in the past from our perspective, and that we would be in the past from their perspective. That's kind of how, but I don't know. I'm not a scientist, so I'm not really sure. But it could mean that time flows backwards in their universe. Could it? Maybe? I don't know. That would be very strange. I have no idea. I wonder if the laws of physics in the anti-universe would be so different that you couldn't even have life form there to begin with. Life would be impossible in that universe because the laws of physics wouldn't allow for the formation of stars and for planets and places for stuff to live. On the other hand, life will find a way, right, Dr. Ian Malcolm? All right. Next up, the James Webb Space Telescope was a huge step forward. It is far more capable than the Hubble telescope. It was launched December 25, 2021, and entered service on July 12, 2022. I could do a whole episode about it and all of its discoveries. It's really cool, and we've gotten some really neat stuff out of it. But one of the important things for this episode is that it can see all the way back to the early universe. It seems strange, but the further away you can see, the further and back in time you can see. The light from a star 1 light year away took 1 year to reach us. So something 100 million light years away will appear as it did 100 million years ago when its light reaches us, because it took that long to get here. At least that's how I understand it, but I'm a dummy, so don't listen to me. Anyways, the James Webb Space Telescope saw something unexpected in early galaxies. It appears that 60% rotate in the same direction. This doesn't really match what science says should happen. According to science, there should be about a 50-50 distribution. If you had somebody in this article I was reading, I forget the scientist's name, I think I quote him further down, but he said that, it's so obvious anybody could see it. And I found that hilarious because, yes, I could see that there were 60% rotating versus 40% rotating, but I wouldn't know that there was anything significant about that. To me, I would just figure, whatever, 60-40 split, looks good to me. But no, apparently this is really significant. So this is an article from iflscience.com, and here's a quote from the Kansas State University team's paper that's talking about this. If the observation shown here indeed reflects the structure of the universe, it shows that the early universe was more homogeneous in terms of the directions towards which galaxies rotate, and becomes more chaotic over time while exhibiting a cosmological scale axis that is close to the galactic pole. Okay. Some cosmological models assume a geometry that features a cosmological scale axis. These include ellipsoidal universe, dipole Big Bang, and isotropic inflation. In these cases, the large-scale distribution of the galaxy rotation is aligned in the form of a cosmological scale axis, and the location of that axis in close proximity to the galactic pole can be considered coincidence. One explanation is that the universe was so all that stuff is saying that there's the universe seems to be rotating on an axis. Kind of weird, right? The universe rotates? Okay, cool. But that's what he says the paper says that's what is suggested by the rotation of these galaxies. One explanation is that the universe was born rotating. That explanation agrees with theories such as black hole cosmology, which postulates that the entire universe is the interior of a black hole. But if the universe was indeed born rotating, it means that the existing theories about the cosmos are incomplete. So in other words, we could be inside of a big black hole. This is not a new idea. Other people have proposed the idea that every black hole is its own universe. But this is the first time, at least that I'm aware of, that they've found actual evidence to support that theory. This is what I meant at the beginning, where that one skeptic was saying, well, it's all a bunch of hogwash anyways, because we can't really disprove it or whatever, so it's not scientific. But if we can find evidence to support the theories, then maybe we can figure some of this stuff out. Maybe it really is possible that we have a multiverse. Or does creation just end outside of our universe? I don't know. This is like, I told you, man, this episode's weird. At least I think this stuff is really weird. Because like the Big Bang, from what I understand, the Big Bang created space-time. Space-time did not exist outside of that, right? Or did it? I don't know. But as far as our local universe is concerned, the space-time in our universe is specific to our universe. So I don't know, man. That's like pretty crazy stuff. So if our universe is not a black hole, that would mean that there's nothing outside of our universe because, and I don't mean nothing as in the emptiness of space, but I mean space-time cannot exist outside of our universe. So if there's another universe out there somewhere, then what's in between these two universes, right? I don't know. It's weird to think about. Am I even making sense here? I don't know. So just to review, I'm pretty sure I've talked about a black hole on this show before. I've definitely talked about neutron stars. I think that was the first mind boggle of the week I did on the very first episode, way back in the day when I talked about, the 1966 swamp gas case. That was a fun episode. I love that one. It's one of my favorite topics. Anyways, neutron stars are kind of like a black hole, but they kind of wimped out. They didn't have enough mass to become a black hole. So a black hole is matter that's so dense and compact that nothing can escape its gravitational pull, not even light. The boundary where nothing escapes is called the event horizon. The event horizon is not the surface of the black hole. That's just the boundary where nothing can escape from the gravity of the black hole. These form when giant stars collapse at the end of their lives. And it makes me wonder, just, my mind goes to silly places sometimes, but in a star-rich area, could enough stars sort of combine with each other so that it was big enough to collapse in on themselves before the star dies out? I don't know. Probably not. I'm probably just misunderstanding how all this stuff works, but right? Kind of like snowballs. If the stars all have gravity and they all sort of like stick to each other, could they all combine? I don't know. Do stars even do that? Who knows? So our sun will eventually become a red giant. However, a larger star with at least 3 solar masses can collapse once it burns through most of its fuel. The burning fuel in the star creates an outward pressure that counteracts the gravity of the star, but when that lessens or slows down, the gravity of the star's mass overcomes the outwards pressure and it collapses in on itself. And all of the mass eventually collapses into a singularity or a single point. That's what the equations say, or so I'm told, but we don't really know what's inside of a black hole because we've never observed it, although there are some pretty smart people who have theorized about it. Here's a quote: "A gravitational singularity is a theoretical condition in which gravity is predicted to be so intense that space-time itself would break down catastrophically. As such, a singularity is by definition no longer part of the regular space-time and cannot be determined by when or where. So yeah, the laws of physics as we know it don't work the same inside of a black hole, or at least according to science, or theory, I should say. So a black hole cannot be directly observed. It can only be identified by the matter that it interacts with. For example, some of them have an accretion disk. As stuff gets pulled in by the black hole, for instance, a nearby star, if you have a binary star system, one of them turns into a black hole and they attract each other, then that star can give off matter that will circle the black hole in a disk as it slowly falls into the black hole, and that's an accretion disk. And we can see them by stuff like that. Now, just to counteract some popular science fiction ideas out there, if our star collapsed into a black hole right now, it would have the same gravitational pull that it has right now because it would have the same mass that it has right now. So this idea of a black hole consuming everything, consuming the entire universe, whatever, that's not really how it works. A black hole has the same mass before and after the transition. Actually, sometimes it'll shed off the outer layers of the star, and then it has a little bit less mass, actually. But either way, a black hole is not going to come and get you. It is what it is. If I turned my desktop computer or my laptop computer into a black hole, it would have the same gravitational pull as it did, and it would not suddenly suck me into it because it's not doing that right now. The mass is way too small. Gravity is a weak force. Anyways, a black hole is a quote here. A black hole singularity is covered by an event horizon, so it is never in the causal past of any outside observer, and at no time can it be objectively said to have formed. So I guess it exists outside time and space. I don't know what that means. It's a quote that I found, and I thought it sounded cool, so I put it in there, but I don't know I have no idea what they're talking about here. All right, here we go. Continuing on. General relativity also predicts that the initial state of the universe at the beginning of the Big Bang was a singularity of infinite density and temperature. So anyways, going back to the findings of the JWST, they suggest that we could be in a black hole, according to the researchers. Obviously, this needs more evidence before we can say that it's true. However, if it is true, it has some interesting implications. Every time a new black hole is created in our universe, a new universe is born. There are many black holes in the universe. How many? I have no idea. There's a lot. Most galaxies have a supermassive black hole in the center, and this sort of implies that all of existence is a series of nested black holes up and down for infinity. But some of them exist next to each other in the same universe, so they're parallel to each other. And this leads to a possible complex structure of multiple or infinite universes that exist above, below, or next to each other. Really, really weird stuff. Fascinating. So black holes can actually theoretically give off radiation. They haven't been observed to do so, but it's been theorized that they can. So it is perhaps possible for something to escape a black hole. Is it possible for life to send some kind of communication, or even for a vessel to travel outside of a black hole or between them? Or maybe we're all just doomed to universal isolation. Could the laws of physics be totally different inside of each black hole? This would give rise to realities that we couldn't even comprehend. We know our laws of physics, but just because stuff works a certain way here, what if gravity was slightly stronger in a different universe or slightly weaker? What if the, forces, just basic forces of physics were slightly tweaked? Then matter might take completely different structures than what we would expect. What would those be? I don't know. You'd have to ask a smart person. I don't know. But it's fun to think about, though. Are smaller mass black holes different than larger mass black holes? So let's say that our universe is inside of a supermassive black hole, which can have up to billions of solar masses, making the event horizon very far away. It would be very difficult to see the edge of the universe because it's really, really far away. But what if your universe or black hole was much smaller, like 3 solar masses? Would it have fewer stars and galaxies because it had less mass to start? Would the structure of the universe be completely different because of the amount of matter in there? Would it be easier to see or reach the edge of the universe because it would be much closer than a black hole made out of billions of stars, or billions of solar masses, I should say? Would it be easier then to send a message or even a vessel into a different universe once you reach the edge? Or would it be impossible to reach escape velocity and escape that universe? Who knows? But it is theorized stuff can escape, so anything's possible. Maybe there's some way that all of these nested black hole universes are connected. Something like an interuniversal wormhole that flows through all of creation. Just like in the movies and the books, communication and travel could be possible between these universes through this wormhole or wormholes. So it's just an interesting idea. It's an interesting idea that we could be inside of a big black hole and that all of the other black holes out there could also be universes. And that would be quite a strange multiverse. I mean, you wouldn't be able to, with our current understanding anyways, you wouldn't be able to ever talk to the other universe. But then again, our universe is rather large, so we'd be fine. Those poor, poor small universes stuck all by their lonesomes. All right, and this is the next one is not really like a scientific idea, but it's just sort of my own thoughts and musings, right? What's outside of our own universe? I've read before that, I mentioned earlier that matter and space-time are inextricably linked, right? Matter and space-time were created when the Big Bang happened. It didn't exist before that or outside of that. You can't have one without the other, right? So perhaps our universe is just a bubble within the larger scope of creation, just one of many bubbles separated by vast nothingness. Not even just empty space, but nothing at all. All of these bubbles together could form some kind of a system. Maybe they're somehow connected to each other, like stars that form a galaxy. Who knows? Maybe they could collide with each other, combine, separate, or otherwise interact with each other like our stars and galaxies do. Could they be continuously collapsing in on themselves and rebirthing into brand new, yet old bubble universes? Maybe this is why dark matter is missing. Many universes pulling from the outside in equal amounts from every direction. Of course, there's no evidence for this, but it's fun to think. There's no evidence observed showing that an external universe exerts any force on our own. If that was the case, it would be pretty apparent. But what if it was equal from all directions, and that's why we're expanding in all directions? So it wouldn't be obvious that it was an external force operating on our own universe. I don't know. But if you believe the scientists who say that there hasn't been an external force viewed or observed, then that would suggest that there aren't any universes out there, and that ours is the only one in this specific space-time construct. However, it could mean that these bubbles are so far apart that they can't interact with each other. Or perhaps that because between the bubbles is nothing at all, not even space, but nothing, not even time or anything, so they're completely isolated from each other. I don't know. This is just some of the things that went through my mind when I was reading through some of this stuff. And it is similar to some other ideas that I'll go over in a bit that are, more well thought out than my ideas, that's for sure. But hey, it's fun to speculate, right? All right, I mentioned earlier the inverse gambler's fallacy. So the gambler's fallacy, actually, I mentioned the gambler's fallacy during the gate program episode. And I misquoted it. I said it was remembering your winnings and forgetting when you lose. That's not the gambler's fallacy. I was wrong about that. The gambler's fallacy is the idea that if something happened more often or less often in the past than expected, it will happen less often or more often in the future. For example, if you have a coin, a fair coin that flips with a exactly 50-50 probability, and you flip it and you get heads 10 times in a row, according to the gambler's fallacy, the next flip should be tails, or at least tails will be more likely because you've had all these heads in a row. But this is actually false. The chance of an outcome on any flip is 50-50. It doesn't matter how many heads happened before this in a row. It could be 1,000,000 heads in a row, and the next flip is still a 50-50 chance. It doesn't matter. So in this case earlier with 10 flips, the 11th flip would have a 50% chance of tails. So that's the gambler's fallacy. And there's a lot of really fun thought experiments and applications to this, but we'll move on because we're doing the multiverse, not the gambler's fallacy. So the inverse gambler's fallacy is, quote, the fallacy of concluding on the basis of an unlikely outcome of a random process that the process is likely to have occurred many times before. For example, if you walk into a room and see somebody roll dice and they get double sixes, that's not very likely to happen, then you would assume that this is not the first time that they rolled the dice. So if you see something extremely unlikely happen, you assume that it's other stuff has happened leading up to that. Whereas we don't know that for a fact. You could very well have just rolled the dice for the first time. This idea was first explored by philosopher Ian Hacking. In his first paper on the topic, he used the idea of argument from design as his main example. The argument from design asserts that the universe is fine-tuned to support life, therefore the universe was created by an intelligent designer. So it's the same thing. You're extrapolating something in the past from current data. So our universe, it seems extremely unlikely that our universe would have the right conditions to support life. Therefore, it wouldn't be possible without some intelligent design, whether that's God or some alien species that created their own universe in a laboratory. Tomato, right? So Hacking argues that while the universe is fine-tuned for life, our universe is part of a long sequence of universes. The fact that ours is fine-tuned means that there were poorly tuned universes before this one, rather than our universe had an intelligent designer. But the way I read it, it's kind of the same fallacy, right? We don't know whether or not any other universes exist. We don't know whether or not any universe preceded ours. Space-time didn't exist before the Big Bang, or so as far as we can tell. So the idea of before and after don't even apply. Even if they did, our universe, which is equivalent to rolling a double six because it can support life, doesn't prove that a poorly tuned universe, or the equivalent of rolling, let's say, a 7, came before ours. It could be that any universe will always be tuned for life because life will find a way. You knew I was going to say it, right? So we don't know. We just don't know. And it's weird because when I was reading the article, it seems like his explanation is the same fallacy that he's talking about to try to disprove an intelligent designer. Or maybe I just don't understand any of this stuff at all, right? Who knows? But I just thought that was an interesting thought experiment. You know, the inverse gambler's fallacy, or the idea that, you know, if you see something improbable happen, that suggests something happened before it. You know, so if you see, let's say you roll 6 dice and all 6 are 6s, you're playing Yahtzee or whatever, and then you would assume that's not the first roll of the dice. So it's kind of a fun idea. All right. We have other types. There's so many different types of multiverses that we couldn't possibly cover all of them, but let's get to Max Tegmark's 4 levels of multiverses. Now, we're going to start getting into stuff that I don't really understand, but here we go. So level 1 is an extension of our own universe. And first we need to define a Hubble volume. A Hubble volume, named for the astronomer Edwin Hubble, or Hubble sphere, subliminal sphere, causal sphere, and sphere of causality, is a spherical region of the observable universe surrounding an observer, beyond which objects recede from that observer at a rate greater than the speed of light due to the expansion of the universe. So, because the universe is not just expanding, but that expansion is accelerating, at some point that will become so fast that it'll exceed the speed of light, and you will no longer be able to observe anything beyond that point. That's kind of what they're talking about here, unless I'm completely misreading this stuff. It seems like it might violate the laws of physics, since nothing can move faster than the speed of light. However, things can move faster than the speed of light relative to each other, maybe, kind of, I don't know. So, well, let's just say that they can. Either way, the boffins say it's so, so it's so. I like throwing that word, the boffins, in there. You know, they use that over there in England sometimes. Instead of, it means scientist, and I think it's a fun word, so I like to say it sometimes. So anyways, this sphere, this Hubble sphere, is based on the point of observation. It's not an actual physical structure in the universe. It's just our own ability to observe the universe. There is a cosmological event horizon beyond which nothing can be observed because it's moving away faster than the speed of light. Really weird. I don't know. I think I'm understanding this, but like I said, I gave you a disclaimer at the beginning and also of this list, because this list gets pretty weird. Anyways, a level 1 multiverse, quote, a prediction of cosmic inflation is the existence of an infinite ergodic universe, which, being infinite, must contain Hubble volumes realizing all initial conditions. Don't ask me what ergodic means. I looked it up and we don't have time for that. You need a lot more terms to define the definition of that one. It's like, you know, you got to go down the rabbit hole, right? Once you look at one thing, ergodic, what's that? Then you find another phrase like phase space. What's phase space? So you got to click on phase space to find that. And you're like, well, I don't understand this either. So I got to click on all this other stuff under the heading of phase space to understand that stuff. And then, you end up going in these loops where it takes forever, and you go so far afield of what I'm trying to talk about on this episode that it's a distraction. And you never get anything done that way. So we'll just say that ergodic means something scientific that I don't understand. So, but anyways, in a level 1 multiverse, the universe will have an infinite number of Hubble volumes. They will not be identical, but have variation in the amount of matter in each. However, because there are an infinite amount of them, somewhere out there, there's a Hubble volume that is similar or identical to our Hubble volume. So in other words, if the universe is infinite, then there will be a place similar to this, but because of these Hubble spheres, we can't really observe each other. Tegmark says, that's whose list this is, says that there should be an identical volume or parallel universe 10 to the 10 to the 115 meters away from us. How big is that? I don't know. Or how far is that? I don't know. And the most important question is, which direction can I go? Wouldn't that be cool if you could meet yourself, you know? I don't know. Maybe it'd be kind of weird. Maybe I'm an asshole and I would hate myself. I don't know. All right, so here's another quote. Given infinite space, there would be an infinite number of Hubble volumes identical to ours in the universe. This follows directly from the cosmological principle wherein it is assumed that our Hubble volume is not special or unique. All right, so you guys got all that? I'm not sure I do, but I think that what he's saying is if the universe is infinite, there will be an infinite copies of our local area. Therefore, we have a multiverse, although it's still contained in the same universe. I guess, maybe, I don't know. Like I said, a lot of this stuff kind of goes over my head. All right, his level 2 multiverse. The eternal inflation theory states that space is stretching and will do so forever. However, some regions stop stretching and form bubbles. These bubbles are embryonic level 1 multiverses. So I guess our universe could be just part of a larger universe that's continuously expanding, but ours stops expanding, but ours is expanding still. I don't know. I have no idea. I don't know, guys. Part of the level 2 version, there's other sub multiverse ideas that fall into this category. One of them is the cyclic or oscillating model, where a big bang is followed by a big crunch, and then the cycle repeats over and over again. Does it repeat for everything or only the bubble universes? I don't know. I'm really confused over here by this one. Another idea under the category 2 is cosmological natural selection. This one is pretty weird. Basically, every black hole is a universe. Each universe can have different rules for how matter acts or the laws of physics work. What if electrons had a -2 charge instead of a -1, for instance? Matter would behave very differently, probably. So each universe is different than the others, and then you can apply population biology theory to the new universes or black holes or something. I don't know. Not going to lie, I don't really understand this one at all. But it sounds really interesting, so I wanted to mention it. All right, level 3, many worlds interpretation of quantum mechanics. And I mentioned this one before when I talked about the, Schrodinger, the guy who tortured cats, because according to his theories, there are actually multiple parallel universes out there. Many worlds interpretation. In brief, one aspect of quantum mechanics is that certain observations cannot be predicted absolutely. Instead, there is a range of possible observations, each with a different probability. According to the MWI, the multiple worlds interpretation, each of these possible observations corresponds to a different world within the universal wave function, with each world as real as ours. Suppose a 6-sided dice is thrown, and that the result of the throw corresponds to observable quantum mechanics. All 6 possible ways the dice can fall correspond to 6 different worlds. In the case of the Schrodinger's cat thought experiment, both outcomes would be real in at least one world. So yeah, this quantum stuff gets pretty weird. And once again, I have to admit, I don't really understand most of it or any of it, but it sounds really cool though. But yeah, that one's basically the traditional multiverse or parallel universes that is often portrayed in science fiction. Level 4, the final level on this guy's list, is the ultimate ensemble. This is Tegmark's own hypothesis, and he says that all universes are equally real. What does that mean? I don't know, but here's a quote. Abstract mathematics is so general that any theory of everything which is definable in purely formal terms, independent of vague human terminology, is also a mathematical structure. For instance, a theory of everything involving a set of different types of entities, denoted by words, say, and relations between them, denoted by additional words, is nothing but what mathematicians call a set theoretical model, and one can generally find a formal system that it is a model of. I don't know what that means, guys, but You know? He says that this, quote, this implies that any conceivable parallel universe theory can be described at level 4 and subsumes all other ensembles, therefore brings closure to the hierarchy of multiverses, and there cannot be, say, a level 5. So he says that's the ultimate level that encompasses everything. What is that level? I don't know, man. What did I just read? I have no idea. All right, another guy, Brian Greene, has 9 different types of multiverses. The first is called quilted, in that we can only exist in an infinite universe. With, quote, with an infinite amount of space, every possible event will occur an infinite number of times. However, the speed of light prevents us from being aware of these other identical areas. It's kind of like the other one in the previous list, right? Where you have these Hubble spheres. The inflationary multiverse, various pockets in which inflation fields collapse and form new universes, very similar to one of the previous ones, right? Brain multiverses, B-R-A-N-E, not B-R-A-I-N. Our universe exists on a membrane or brain, which floats within a higher dimension called a bulk. And there are other membranes in this higher dimension. These universes or membranes can interact with each other. They can collide occasionally, creating a Big Bang, but a Big Bang doesn't happen very often. My question is, wouldn't all of the brains over time combine and collide with each other and create larger and larger universes? Would it ever get to a point where there's so much mass in these universes when the Big Bang is supposed to occur that it could no longer occur, and then we have the end of creation? I don't know. Fun to think about. All right, another category, cyclic. This is a multiverse that has multiple brains that have collided and big banged. They bounce back and forth and pass through time until they are pulled back together again and collide once more, creating a new universe. So, I mean, this is similar to another, what we talked about one before, where you have a big bang, then a big crunch, and then another big bang, and then it repeats. The landscape multiverse. This one is based on Calabi-Yau spaces from string theory. I looked it up, and it makes zero sense to me at all. But basically, Calabi-Yau spaces have multiple dimensions, 6 dimensions, 10, 11, 12 or something. I don't know, whatever. Quantum fluctuations can drop stuff to a lower energy level or a lower dimension level and create a pocket with a set of laws different than the surrounding space. In other words, it sounds to me, now I don't understand this stuff at all, but it sounds to me like perhaps you have higher dimensions and stuff from that higher dimension can somehow protrude to lower dimensions and only exist in those dimensions, possibly temporarily. And so our three-dimensional universe, there is a much, larger structure of multiple dimensions that exists outside of that, but we can't observe it. I think that's kind of what they're saying. I don't know. All right. The quantum multiverse. Every time a diversion event occurs, a new universe is created. And once again, this is like the quantum stuff that, Schrodinger's stuff, where you have multiple universes that occur simultaneously, just like the ones you see in science fiction movies. The holographic universe, this is more string theory stuff. Quote, the description of a volume of space can be thought of as encoded on a lower dimensional boundary to the region, such as a light-like boundary, like a gravitational horizon. Yep, no idea what that means. It sounds really cool, holographic, multi-dimensional, whatever, I don't know. Okay, simulated multiverse. Basically a multiverse that exists as a computer simulation, and there's other ideas like maybe a universe that's been created in a laboratory somewhere. But this is, the simulation hypothesis, basically. and the ultimate category that contains every mathematically possible universe, very similar to the previous category 4. All right, and then the last type of multiverse I have for you today is M theory. If there are 10 or 11 space-time dimensions, once again a string theory kind of a thing, our universe could exist on a larger multidimensional object or space, which could have other universes as well. And that sounds similar to the other one I was talking about with the Calabi-Yau space or whatever. So it's probably some overlap there. But yeah, so that's just a basic overview of all the different possible multiverses. Each one of these I could do a whole episode or more on each one of these types of universes. There's a whole lot of sciencey stuff and ideas around them. There's a lot of discussions around them. There's a lot of really cool stuff out there, but I've kind of wanted to do a bunch of them rather than just do one of them. Personally, the one I find the most fascinating is the baryon asymmetry or the antimatter mirror universe, because there's really good evidence that antimatter is missing from our universe. So it's supported by evidence that this could exist. We don't know that it exists, but it's one possibility that could explain this matter asymmetry. So that's kind of my favorite, but they're all pretty interesting. Well, at least the ones where I kind of understand what they're talking about, But there's some really cool ideas here, and this is a really fun one to read about, and it kind of makes me want to study physics, because as I was reading this, I was reading all sorts of different ideas and things that I could only just skim on because, the show has to happen at some point. But man, there's so much fascinating science out there. And there's so many smart people doing really smart things. I would love to be able to study up on it so I could understand some of it. That would be really cool. Because, we're unlocking, not me personally, but collectively we are unlocking the secrets of the universe. That's really cool stuff, guys. All right, well, that's all I've got for you this time. Until next time, keep it strange.